Welcome to Astrum Space and Galaxy, your gateway to the wonders of the universe.
Scientists have an issue with Polaris. In the distance, the North Star's constant place in the nighttime sky has led us for centuries. But close up, it appears to act in confusing erratic turns. The closer we examine it, the less it adds up. Polaris doesn't trespass like our star models expect, and it is remarkably difficult to obtain simple measurements for it. How can a star so evidently visible to the naked eye be evasive to our scientific instruments? Sounds rather ironic. So let's dive into everything we know and don't know about this mysterious star. You're watching Astra? Join me today as we uncover Polaris's secret companions, delve into its odd behavior, and unveil why this star might redraw our map of universe. No, seriously. Wait and see. Finding the North Star, it's a moonless summer evening and you've walked to your favorite stargazing location. Looking up, Zemayar, and it includes the Big Dipper, a group of 7 stars. In Theorem of a Ladle, you trace the two-pointer stars up and up until you strike a noticeably bright star in the sky. That is Polaris. It rests almost precisely above Earth's rotational axis. So while all other stars seem to wheel around the sky, this one remains stationary. At the North Pole, Polaris seems nearly directly avert. As you go south, it seems lower and lower in the sky until Yoriak, the southern hemisphere, and it disappears from view behind the horizon. But while we've been trusting Polaris to guide us, around the world we find that Polaris itself is much more mysterious and much more complex than anyone ever thought. To us down here on Earth, triple star system Polaris looks like a single, constant point of light that isn't unless you look through a telescope. In 1779, William Herschel did, and he found Polaris also had a second star, Polaris B, in a large orbit. 120. Years later, in 1899, astronomer William Wallace Campbell observed Polaris A to have variable radiovesity, indicating it could have another companion star, one not observable with a telescope. In 1929, a spectroscopic observation confirmed it, and only obtained our first pictures of tethered Polaris star, Polaris AB, in 2006. Thanks to the Hubble telescope, these 3 stars are gravitationally bound in a triple star system. The brightest member, Polaris AA, is what we refer to as the North Star. It is an advanced yellow supergiant 5.13 times Sun's mass and 46 times larger. If it were put into our solar system, it would extend more than halfway to Mercury, 2.8 billion km away is its close friend, Polaris AB. In combination, Cecito stars are a binary system which makes a complete orbit every 29.6 years. That third star, Polaris B, orbits around the Centaur pair every 40,000 years at a distance of 386 billion kilometers. That's roughly 24 times farther away from us than Voyager 1 is after 48 years of flight. Polaris B and Bay are both yellow-white dwarf stars, roughly 500 times less bright than their main star. Polaris BH 1.39 times the mass of our Sun, while slightly smaller Polaris ABH Ace 1.26 solar masses. But Polaris's 3-star system is not the least interesting thing. Primary star Polaris AA is part of a rare category of stars called Cepheid variables, which as it happens are the secrets to charting the universe. Cephids. Standard candles. An astronomer named Henrietta Leavitt worked at Harvard College Observatory studying the Little Magellanic Cloud. In 1908, she was studying Cepheid variable stars in a given phase of stellar development, which pulsate periodically increasing and decreasing in reliable cycles. She found there was a direct correlation between how luminous a Cepheid looks and how long its pulsation period is. The luminosity of the star. The longer it takes to finish one pulse of pulsation, this made Cepheids into ordinary candles, objects, whose intrinsic brightness can measure by simply determining their pulsation period. Since we now know how luminous they really are, we can't compute how far away they have to, but depending on how luminous they look to us. It's similar to knowing the actual wattage of a light bulb. The dimmer it appears, the further away it has to be. Cepheid's become a key rung in what astronomers refer to as the cosmic distance ladder, our tool for estimating distances around the universe. Prior to the period luminosity relations revolution, we could only estimate objects a few hundred light-years away with stellar parallax. A measurement of how far a star moves in the sky is seen from Earth, but with this recent discovery, sudden scientists were able to measure intergalactic distance in millions of light-years. Now we could utilize nearby techniques such as parallax to calibrate seafoods, then utilize aphids to determine distances to other galaxies, and in turn, help you calibrate even further away markers such as STIP 1a supernova. Polaris AA is weird as being the closest seafood to our planet. You'd think that would make Polaris a gold mine for space studies. It could help us calibrate the size, age, and fate of the universe. Everything from distance to Andromeda to the rate of the universe's expansion. But here's where things get complicated. There's still some debate about how fast exactly our universe is expanding. Measure it one way and the number is 73 kilometers per second per megaparsec. But measure it another, and you get 67 kilometers per megaparsec. In an article from our advertising sponsor, The Economist, learned that this difference has actually strengthened as more data came out. So something might be wrong with our models. Personally, that fascinated. And you should check out their article on the topic if you want to dive more into that mystery. I like The Economist. It's a great independent news source that offers more than just breaking news. It gives insight and analysis on the things that matter. Turns out, Polaris AA is a very strange food for a number of reasons. First of all, amplitude is unpredictable. Scientists observed that the difference between its brightest and dimmest points declined between the seed 1960s to 1990s. From above 0.1 to below 0.05 magnitude, it stabilized and was steady for whilst before beginning to rise again in the year 2000, a trend never seen in any other seafood, but it's not only his amplitude that's raised eyebrows. For the 150 years, we've been observing it. Polaris's period for round for days has been increasing by 4.5 seconds per year. That's an incredibly fast rate of period change for a seafood, which suggests Polaris is evolving quickly. One theory astronomers have for this unusual behavior is that Polaris might be entering an unstable phase of its life. All stars go through an unstable phase when they leave the main sequence, but they don't necessarily all become seafoods. They become as determined by a number of characteristics such as its luminosity and pulsation period, among other factors. Most seafoods experience sea-free major instability episodes in their life. The first occurs very quickly, lasting between 10 and 100,000 years. It occurs when hydrogen fusion in the center has ceased and the star departs main sequence towards bumming. A red giant or supergiant, it's the least researched of the instability phases, since it's so short relatively speaking. The second instability happens when the star starts burning helium in the core, stabilizing the star and causing it to burn hotter and bluer in color. This takes anywhere from 100,000 to 10 million years. When the star eventually runs out of helium, swells up again and is unstable for the third time with a similar time scale to the second phase, almost all the seafoods we've had these unstable stages have been in thirst-canned or third stage, so their conduct is comparatively predictable. But trapping a seafood on their initial instability is very uncommon, and their behavior in this state is far less understood. There is no agreement on which stage of instability. Polaris is, some say it's in the first while others that it must be in the third. And no sooner had these theories arisen, tocant for the changing period, Polar suddenly reversed the trend. Since 2010, its period has been shortening year after year, and nobody knows why. We believe it could be because of Polaris disturbing it whenever they pass each other at their closest point, but no one is for sure. But even more fundamental than that, there's still a key piece of the puzzle missing to full understanding. Polaris properties. Asterisk something embarrassingly simple that's proven. brutally challenging to solve. Are our models wrong? You might expect that with modern technology. Measuring the distance toward North Star would be straightforward, but it's actually trickier than you might imagine for a few reasons. First of all, Polaris is hundreds of light years away. The farther away a star is, the smaller its parallax shift will be. For context, the Hipparcos mission of Theonides measured Polaris parallax to be 0.00754 arcsec, or 2.09 for asterisk 10⁻⁶. Incredibly tiny movement. On top of that, Polaris is bright enough that it can't avert our detectors, causing our 1244 readings to be unreliable. Add to that the fact it is a pulsating C-fared star with a close companion, and brightness-based distance readings become even more complex. All of this makes Polaris' distance from Earth surprisingly difficult to quantify. Estimates have varied from 323 to 520 light years away, and there's still no overall consensus in the scientific community. For instance, Hipparcos mission put Polaris at 434 light-years, while more recent Gaia data from ESA puts it at 447 light-years away. Without a good sense of how far Polaris is, making estimates of other properties as mass, radius, and luminosity is problematic. The estimates of mass and radius that I provided earlier are based on Gaia data. Beautif, we used other inputs. Widget, quite different predictions. And to make things worse, the estimates we do have of Polaris, age, mass, and pulsation, period, don't match our stellar evolution models at all. And dance more. We don't really know why. For instance, Polaris AA seems to be much less massive than we predicted and muckier than its companion. Polaris BWELL, return to this age difference in a moment. 1. Such reason is thelements of the stellar evolution models themselves. First of all stars rating. This rotation can have significant effects on stars' structure, evolution, and pulsation behavior. But modeling rotation is very complicated, does include many unknowns. So manusers simply leave this important factor out of their stellar evolution models. For a star like Polaris AA, this emission could be causing majors in our evolutionary predictions. Another explanation is that Polaris AH has lost mass in its evolution, possibly through solar winds or interactions with its companions. Mass loss would account for the star's swift period change and might account for some of the differences with evolutionary models. Scientists have attempted to estimate mass loss with some research, putting it at 2 septillion kilogram per year, that is a 2, with 24 zeros behind it, but as yet there hasn't been very persuasive evidence to vindicate this theory. And last but not least, 2024 observations with the Charara array revealed John star spots on Polaris's AA surface. The spots are in line with the existence of a magnetic field which may also influence the star's puls. If we lack important physics in our understanding of how these stars develop and behave, it may impact the accuracy of seafoods as standard candles. An I4 model of seafoods is an error. It's an ISER map of the universe. The age paradox. Polaris is pulsating strangely rapidly. We're not certain how far away it is, and it's making us question our models for stellar evolution. And if that weren't enough, Polaris has yet another trick up its sleeve. Recall that age discrepancy? If Polaris A is AA and Polaris B are gravitationally bound as they appear tobe, they must most likely form together. This means we'd expect them to be the same age. Yet our observations tell us otherwise, assuming 447 light years to be the distance. Polaris AA is around 50 million years old. But it is estimated. Polaris B is 2 billion years old. So something must have happened here. A couple of theodoshes tried to unravel this. Not one is merely that Polaris B is not a companion to Polaris A after all. Despite rigorous evidence to the contrary, but another more attractive notion relies on a phenomenon we've been aware of since the 1950s. Globular clusters are dense environments of stars that all formed around the same time. And yet in 1953, Alan Sandijanist, some stars, appeared much younger than others, bluer, hotter, and more massive. He named them blue stragglers. We think they form as their salts of star collisions when binary stars merge. The result is a star that appears much younger than its true age. It's possible that this is what happened to Polaris AA. It could have been revitalized by an impact with Anno Thurster, once in close proximity to it. Although this merger theory is speculative, it illustrates how the Polaris system defies our picture of stellar evolution and binary star formation. At the end of the day, this age difference is still one of the big mysteries revolving around the Polaris system. Polaris won't be the North Star forever, although the Polaris star is our Earth star today, it won't remain so forever. Earth's rotation axis like a top. Consequently, our celestial pole walks about in a closed circle, passing by various stars, some 14,000 years ago. The celestial pole was pointing towards the bright star Vega, and it will return again to that position in some 12,000 years. For millennia, Polaris has been guiding human beings over oceans and deserts, but today, it guides us in another way, compelling us to face what we still don't know about the stars, the universe, and even our own scientific boundaries. And as the next installment of Gaia Data draws near, said to be released in mid-2026, we might finally have some more definitive insight into this confounding star system. Thanks for watching. If you enjoy this video, you might enjoy this one on Proxima Centauri, our nearest star. I'll see you next time.